In Unit 8, we start to use what we've learned about vectors to actually interact with 3D objects. We know how to work with some vectors in 3 dimensions, but you remember I've been trying to stress from the beginning the difference between a vector, which is kind of like a direction and a magnitude, kind of like a set of instructions, as opposed to a physical object like a point or a line. Uh, so you can see the same analogy we used in Unit 7 we're going to use again, which is to say we're going to start with some stuff in 2 space, and then we're going to sort of evolve that into 3 space. Now, you, of course, already know many different ways of writing a line and representing a line in 2 dimensions. We know mx plus b form. We know standard form, right? Like these are both good ways of representing a line. In fact, in 2 space, you know, 2 points will do it, right? If you know 2 points, you can just go line AB. However, when you go over to 3 dimensions, these lines don't really work anymore. And if I try to say like y equals m, 3z plus 1, I don't get a line, I get a different object, right? I get a surface, what's called a plane. And so, again, when you ask GeoGebra, like, okay, how do I make a line? So let me get rid of this for a sec. So let's delete all of this stuff so it's not so confusing. Okay. I'll just make a new one. So suppose I wanted to create a line. I know one way to make a line is I go A, 1, 1, 1. B is, 2, 4, negative 1. And I can go line AB. Now, this is what it comes up with. 1, 1, 1 plus lambda 1, 3, negative 2. And that is the equation of a line. If I type line, you can see what it might want. It says point and parallel line, or point and direction vector. Oh, you can't see that, I'm sorry. Sorry, if I type line, this is the point I was just trying to make. It can do it with a point and a vector, a point and a parallel line, or a point and a point. So what we're going to do today is we're really just going to concentrate on how to understand this equation in 2 dimensions so that we can sort of upgrade it to 3 dimensions when we need to. So let's consider parametric and vector equations of a line in 2 space. Again, you already have a couple of ways of making a line in 2 space. This is not because I'm going to ask you a lot of 2 space questions. It's just because when you know this, you'll be able to adapt to 3D more easily. So there's a couple of ways you can write a line in 2D. You can do what's called point slope form. So y minus a known point, the y value of a known point, equals m times x minus x value of a known point. The slope y-intercept you're probably most familiar with, y equals mx plus b, and then the scalar form, or the Cartesian form, standard form, ax plus b y plus c equals 0. Another way to define a line is as a point with a vector. And you can imagine this by, if we think of this line here, right, you can another way to express this line is as a vector sum. Okay? You need a direction vector that is parallel to the line, which would kind of correspond to the slope. And then you would need a position vector that points you from 0, 0 to the line. And if you add those 2 vectors together with all the different possible scalars on M, you would get every point on the line. So let's see if we can demonstrate this here with this example. So this line you can see looks like rise 1, run 2, so half x plus 5. So y equals 0.5x plus 5. Okay, and we know it goes through the point 2, 6. Right? So that's what we've got. Now we need a direction vector that's parallel to the line. Okay. A direction vector that would be parallel to this line would be any vector parallel to the line. So let's make the easiest one we can make. To get from D to C, right, the direction vector, so we're going to call it M, would be 2, 1. Right? And that would be parallel to this line because to get from D to C would be to go over 2 and to go up 1. Notice if I had put D here and I go over 4 and go up 2, it doesn't make any difference. That would work just as well. It doesn't matter what point you pick. You just need to find the direction of the line that you can express as a vector. So I've done that. M is our direction vector. Now I need another point. I need what I'm going to call RO, which is a position vector that gets me to a point. And what I'm going to say here is vector from O to C. So this is RO, right? And it's 2, 6, and it's not complicated. It just corresponds to the point C, which is also 2, 6, right? Now, watch what happens when you add, so RO plus a scalar multiple times M. Okay, so RO plus A is my scalar multiple, times M. Okay, and then what I'm going to do is I'm going to go a point, P, let's say, is equal to O plus RO plus AM. And then let's trace this point. Okay, so look at point P. First of all, point P is on the line, right? Because you can imagine it as O, like RO got you to the line, and then M moves you up and down along the line, right? And if you look at all the different scalar values, all the different scalars I can multiply M by simply fill in the missing points of the line. Okay, so this is a different way to understand a line. It's not, it looks complicated. It is not. It's the same thing as a slope and an intercept. Or a slope and a point. You're just expressing it in vector form such that adding up the position vector plus a scalar multiple times the direction vector gives you all the points along a line. Okay, and that's what it says here. So again, to be parallel to this line, you'd need to go over 2 and up 1. So we say M is 2, 1. Again, feel free to use 4, 2 or 3, 1.5 or whatever. And then you simply finish the triangle. And what do I mean by finish the triangle? So start with RO, then add the direction vector M, and then connect the two. And wherever you end up, that will be a point on the line. And all the possible destinations of that vector will be all the different points on the line. Okay, so the closed triangle can be represented by this vector sum. S is parallel to M, and it is a scalar multiple of M. So again, we're just replacing S with, K. M, right? And that's the equation of a line in 2 space. They're going to use T as their parameter, which I'm going to start doing as well. It's just the way I'm accustomed to using it. So T is a parameter. It's any real number from negative infinity to infinity. The line is represented by a position vector, which is basically just corresponds to a point, plus T times a direction vector. Okay? And if you think about what it did in 3 dimensions, it didn't use T, it used lambda, but it's the same idea. It picked one of the 2 points I gave, which was 1, 1, 1, and then it did lambda times the direction vector, and if you look at how it got the direction vector, it just did destination minus origin for these 2 points. So we're going to do the same thing. We're not really going to work in 3D today too much, right? I just wanted to make the analogy so you can start thinking about it. But this is another way to express a line. A line is equal to a position vector plus T times a direction vector, where T is any real number. This is a really good thing to remember. The direction vector corresponds to the slope. So the slope would be rise over run. But if you think about the components of the direction vector, it's run first and then rise. So if you just do m2 over m1, you would get the slope. Okay? Now, that's the vector version of a line. There's another way to express this, which is simply to take this equation and separate it into two equations where one only looks at x and one only looks at y. And if you only look at x, you would come to the conclusion that x is equal to xo, which is the known point, plus t times m1. Right? Just look back up here. xo plus t times m1 gives you the x coordinate. yo plus t times m2 gives you the y coordinate. So this is just a way that you can express a line using what we call the parametric equations, where x, y, and z, when we need z, will be isolated. Okay? So the constant term on the right are the coordinates of a point, and the coefficients of t are the direction vector. Okay, so again, let's just take an easy example. So before we go any further, let's just say express y equals 1/3 x plus 1 as in vector form and in parametric form. Okay, so let's write it as a vector. So if the slope of the line is 1/3, then the vector m, right? Right? Okay. This means that vector m is equal to the run and then the rise. Okay, 3, 1. Now, again, it doesn't have to be 3, 1. You could make it 6, 2. Or you could make it -3, -1. It makes no difference because all of those things are parallel. So 3, 1, you might as well just pick the simplest one. M is 3, 1. Now we know the y-intercept of this point is 0, 1. So we know that so let me just get this right. So RO vec is equal to 0, 1. So the vector equation of the line would be R vec equals 0, 1, which is the point, plus t times 3, 1, where t, I was hoping that would work. T, it's in the other symbol somewhere. I'll just use this one. Looks close enough. Okay, where t is some real number. Now, let's just check that I did this right. So, I'm going to draw y equals 1/3 x plus 1. I'm going to draw this now. 0, 1 plus t, 3, 1. So just to show you how to do this on GeoGebra, you make a new vector m, which is 2, 1. And then you go a point, which is 0, 1. And then you say line AM. Okay, and oh, I'm sorry, I definitely made an error here. I said 1. I typed 2, 1. I should have typed 3, 1. So sorry. Just go back and change my direction vector to 3, 1. There, okay. And now you can see the line that we wrote in normal form, like mx plus b, and the line I wrote in vector form are the same. Okay. Now, in parametric form, this is really easy. You just look at all the x coordinates, 0 plus 3t. You look at all the y coordinates, 1 plus 1t. And again, you should say t is an element of real numbers after this. Okay, and that's it. That's the vector and parametric equation of a line. Okay. Okay, what properties do these things have? Where possible, reduce the direction vector into integers. I would agree with that. I mean, there's no reason, for example, to use like 1/3 and 1/9. Like, you could do that. It would work the same. Like, if I go back here, I could change this to 1/3 and 1/9. And nothing changed. It's the exact same line. But you might as well use the simpler versions, right? You might as well use 3, 1. There's no reason not to. So reduce the direction vector where you can to integers. If two lines are parallel, then their direction vectors must be parallel. which means that one direction vector is a scalar multiple of another. So this is a really, really useful property. Okay, to determine that lines are parallel, you simply compare their direction vectors. An even more useful property, two things are perpendicular if their direction vectors dot to make 0. Okay? Hugely important. Both of these things are hugely important. All right, the vector equation of the x-axis. Okay, well, the x-axis passes through the point 0, 0, and it only moves left and right. It does not move up and down. So the vector equation of the x-axis would be 0, 0 plus t, 1, 0. It could move anywhere you want to the right if t is a positive number. It could move anywhere you want to the left if t is a negative number, but it can never move up and down. Similarly, the y-axis would start at 0, 0, and it would be parallel to 0, 1, right? Because it could move anywhere up and anywhere down, but it can't move at all left or right for the y-axis. So again, just a couple of things to take note of there. It says write a vector equation and a parametric equation through this point with that direction vector. So again, the line, we say r vec is equal to the point, -4, -3, plus t times the direction vector. That's it. Again, it's really simple, right? It's just you just kind of got to get used to it. The x parameter would be -4 minus 2t. The y parameter would be -3 plus t, right? And again, in all of the above, I'll just like copy. I don't know. Can I just say this once and you'll remember it every time? T is an element of real numbers for both of them in either case, right? So there's vector form and there's parametric form. I'll just change parametric to a different color. Okay, so write a vector equation and a parametric equation. Very, very easy. You know, that's it. That's all you need to do. It's just about remembering where the parts go. Okay, write a vector equation and a parametric equation that passes through these 2 points. It's slightly more challenging, but let's consider what we know. A is 1, 4. To make an equation of a line, we need r vec is equal to a point plus t times m1, m2. Right? We just don't know m1 and m2 right now, but we do know a point. By the way, you could have chosen b as your point just as well. That would be fine. To get the direction vector, right, m vec is equal to destination minus origin. We know a destination and an origin on this line, which is, let's say, 3, 1 is our destination and 1, 4 is our origin. Then vector m would be equal to -2, positive 2 and -3. And that would be our direction vector. Now again, you could have taken, A as the destination and B as the origin instead. It would be totally fine. That would also work. Any scalar multiple of this would still work. I'll just put in brackets, or you could use -3, 2. Sorry, no, you can't do that. Sorry, I'm messing that up. Or if you'd done it the other way, you would have got -2, 3, right? Which is a scalar multiple of the first one. Anyway, so this gives us the equation of the line now. So the equation of the line is just this plus 2, -3. And that would be the vector equation of a line that goes through those points. Let's prove it. Okay, so let's make a direction vector. M equals 2, -3. And then I'm going to go line that passes through the point 3, 1 and has a direction vector m. Now, if I've done this right, it should pass through 1, 4 and 3, 1. So where's 1, 4 and where's 3, 1? Okay, and it does. Okay, so there you go. The parametric equation, again, oops. The parametric equation would just be x equals 1 plus 2t and y equals 4 minus 3t. And again, t is some real number. Okay, so there you go. Determine the coordinates of 2 points on the line other than A and B. So where would be some other points on this line? To generate a point on a line, when you know the vector and or parametric equations, make up a value for t and substitute. So, for example, if we wanted to find a point, let's find a point when t is equal to, so I'm going to take my equation again, which is right here. And I'm going to suppose that t was equal to 2. If I did that, I would find that I have 1, 4 plus 2 times 2, negative 3, which is 1, 4 plus 4, negative 6, which is 5, negative 2. So I hypothesized that the point 5, negative 2 should lie on this graph, and it does. Okay? We can make up another point. Suppose t equals negative 10. You can do whatever you want. You can make it negative 1 if you want. You can't make it regular 1. If you make it regular 1, you're just going to run into the other point, right? You're going to go from 1, 4 to 3, 1, and that's not a new point. So don't choose 1, but choose any other number. Anyway, if t is negative 10, you have 1, 4 plus, or let's say minus 10, 2, negative 3, which is 1, 4 minus, or plus, let's say, negative 20 and 30. And there you would have negative 19 and 34 ought to be on this line. And it is. Okay? So you can easily generate more points. You can generate as many points as you want or might need. Just simply make up a value for t and plug it in. Right? Remember, t is like a scalar multiple. It's how you would stretch the direction vector to connect to every single point on the line. So any value for t you use will generate a point on the line. That's how this works. Okay, graph the line, draw the closed triangle that represents the vector equation. I'm just gonna, I'll do that here using the GeoGebra. So again, my direction vector is m. Let's maybe it would be good to illustrate it with this weird point I drew d. So what I'm going to do here is let's say RO is the direction vector that gets you to A. So in this case that would be 1, 4. Okay, so there's RO. It connects you with A. Then I'm going to draw negative 10m. That gets you all the way over there. Then I'm going to go RO plus U, and that gets me to the point D. Now, I'm thinking actually this is looking a little, I think this is just a bit too far away. So why don't we say negative 3 so we get a better diagram. Okay, and then the point D would be, well, let's see. So O plus V plus RO. Oh, sorry, V was the vector sum. I'm sorry, I should have said U. It's like looking at that like it double did something there, but okay. Anyway, so let's get rid of some of this stuff. So B and C, and so I'm gonna let's hide the label for this one. Let's hide the label for. Actually, let's rename this to R because that would be vector R. This is vector RO over here. This is the direction vector we had. However, this is the direction vector I used, which was negative 3m. So I kind of I stretched m by a factor of 3 this way, then I added the position vector to get me to A, and that got me to this point E, which is the other side of this triangle. So let's say if they wanted this in sort of triangle form, we draw segment EA, and I'll hide the label for that, and then let's just, so vector RO, vector R, and vector, and this segment, let's just change all the colors of these ones to red or pink, and then you can kind of see. Make them a bit thicker. Okay, so that's what it would be in triangle form. So take this and sketch. Okay. Again, you don't have to draw with a negative 3. I just chose to. You could draw it with a, +2, whatever you want. And the triangle is not unique. I mean, everybody's triangle could be different and still be right. So you just draw a triangle that works. Okay, find the vector equation and parametric equation for each line. It passes through 2, 8. So immediately, as soon as I see it passes through 2, 8, I'm going to go RO vec. Sorry. Is equal to 2, 8, right? So all I need is any point will work, and then it has to be parallel to that, which tells me that m is equal to 4, -2, which actually is the answer. It's just 2, 8 plus t, 4, -2, where t is some real number. Oh, there we go. It is there. Element of, so /in. I'll try to remember that. Okay. So that would be the equation of the line that we're looking for in that situation. It has that point, but it has that direction vector. Okay. Here we go. It has to pass through 2, 8, and it has to be perpendicular this time to this other line. So again, if it passes through 2, 8, then RO is 2, 8. Now m, we don't know what m is, but we do know that if you were to dot, it's just /dot, right? Oh, /bullet. Okay, so m dot -1, -2 equals 0. We do know that. So again, you can solve this if you like, but an easy thing to remember is that if AB, so let's just write it as a law. A comma B is perpendicular to -b comma A. So to make a perpendicular vector, the simplest thing to do is swap the x and the y and then change the sign of one of them. So you can change the sign of either one, but just one of them. Don't change the sign of both of them. So for example here, our vector m, I'm going to say our vector m is 2, -1. I could just as easily say it's 2 positive, -2 or +1. Right? It doesn't matter. Both of those are the same direction, right? This one says go 2 right and 1 down. This one says go 2 left and 1 up. They're opposite vectors. Like all they're doing, they would be. But for what we're doing, which is scaling them by an infinite number, or an infinite number of numbers, it doesn't matter which one you choose. So a perfectly good answer for this one would be r vec is equal to the point 2, 8 plus t times the direction vector. Okay, where t is some real number. Now again, let me demonstrate this one quickly. So let's go what we were supposed to do. So it's supposed to pass through 2, 8 and be perpendicular to this other one. So 3, 3 plus -1, -2. So I'm going to say m1 is -1, -2. And then I'm going to go line that passes through 3, 3 that has that direction vector. Now the line we are drawing has a direction vector of 2, -1. So m is equal to 2, -1. And it has to pass through 2, 8 with a direction vector of m. Now, if I've done this right, these two lines should connect to one another at 90 degrees. And it looks good. It looks that they do. Well, I mean, it says 270, but you get the idea. I mean, if it did the shorter angle, it would have been 90. Yeah, so sorry. You think with a 50% chance to every once in a while get an angle measured the right way, I would get it right, but I almost never do. It's a 90-degree angle, right, where they meet. So the two lines that we created have the property that we were asked to find. Again, a perpendicular vector, remember, it is very easy to make one. Just swap A with B and then make one of them negative. Again, just a very simple test of this. If the first number was 3, 7, then you know that m1 and m2, right? If you dot this out, you'd have 3m1 plus 7m2 equals 0. So the easiest way to do this is make this one a -7, but keep this one a +3, and then you get, negative 21, positive 21, you get 0. So really easy. Switch A with B and change the sign of one of them. Okay? Okay, determine whether the following points lie on this line. Now this is an interesting question. A point will lie on a line if the same value of t works in both parametric equations. So for example, in the first, so let's write the parametric equations. X is equal to negative 2 plus t, y is equal to 1 plus 2t. Now, the first point, we're going to plug it in. Negative 4 equals negative 2 plus t. Again, it doesn't take much work here to see that negative 2 is t. Now, in the second parameter, right? So y equals 1 plus 2t. 2t again. Let's just write that down. Negative 3 is equal to 1 plus 2t. When we solve this one, we get negative 2 equals 2t, and we get negative 1 equals t. Now, since this equation says t has to be negative 1, this equation says t has to be negative 2. Since these do not agree, since the two parametric equations do not agree, the point is not on the line. Okay, again, let's do a quick demonstration. So, to draw this line, I need the point, so negative 2, 1. So let's go line. Oh, I see. No, I can't do that. Okay, so m is 1, 2. And then I need a line that joins the point negative 2, 1 with that vector. Okay, and then the question was, is negative 4, negative 3 on that line? It is. So that would tell you that what I did was wrong. So let's just look back quickly and see what I did. So negative 4 equals negative 2 plus t. Bring the negative 2 over. You get, I'm pretty sure that's right, so maybe this is what's wrong. Negative 3 equals 1 plus 2t. Oh, right, of course. When you bring 1 over, you don't get negative 2, you get negative 4, and then you both get t. So let's correct my conclusion. Since both parametric equations work with the same t value, the point is on the line. Okay? That's one way you can do it. Another way you could do it is you could do destination minus origin and then check if they're scalar multiples. I mean, really, that is the same thing, but anyway. Let's try with b. So with b, I'm going to go, the x-coordinate is 3 equals negative 2 plus t, so 5 equals t. Right? Just bring the negative 2 over. For the y-coordinate, it's a 5. 5 equals 1 plus 2t. 4 equals 2t. 2 equals t. So the values of t do not agree, so the point is not on the line. And again, I should be able to sketch 3, 5 on my diagram here. And it's not there. Right? It does not match up with the line. Which of the following pairs of lines are parallel or perpendicular? Okay, so these two are, so these lines, so over here, let's see if I can move this down. No. Okay, these lines are parallel. Since let's call, yeah, that's okay actually. So the second line's direction vector is negative 2 times the first line's direction vector. Because I can express them as scalar multiples, right? Scalar multiples equals parallel vectors. Okay, so they're scalar multiples, therefore they're parallel. Now these two, you look at this, you go, to get from 2 to negative 6, you'd have to multiply by negative 3. But if you multiply 3 by negative 3, you do not get 4. So these are non-parallel. These are not parallel. Now that they're not parallel, let's try to dot them. So M1 vec And then let's dot with M2vec and see what we get, right? So we get 2 times negative 6 plus 3 times 4, which is negative 12 plus 12, which is 0. These lines are perpendicular. Dot equals 0. Okay, so you dot the direction vectors and you get 0. That's it for today. So again, I want you to go over the two ways of writing a line, vector form, parametric form. Try some of the homework. See if you can start imagining how you would use these things to describe three-dimensional objects. So that we can start moving on to lines in 3D, which is the main unit, the main purpose of this unit. Okay, so any questions, please post.